Variation applications. First, weight on Mars. We're told that the weight m of an object on Mars varies directly as its weight e on Earth. If we're given variables, then we're going to use them. So this first thing that we want to do is just write out what this means algebraically. M varies directly as e, so m is equal to some constant of proportionality times e. Next, we're given an ordered pair, a person who weighs 95 pounds on Earth. That's telling us that E is equal to 95 when this person weighs then 38 pounds on Mars. So E is 95 when M is equal to 38. So we're given one ordered pair, and we're going to plug these values in to find K. So just like the previous example, our first step is to find that linear function that relates the weight on Earth to the weight on Mars. So plugging these in gives us 38 equals K times 95, and then dividing both sides by 95, we get 38 over 95, which we could either reduce. You may or may not recognize the common factor of 19 here, so that this is in fact equal to 2/5, or you might just get a decimal approximation and call it 0.4, either way. Let's call it 0.4. 0.4. So now, just like I did in that previous example, I'm going to bring m and e back as variables and only plug in that value for k, so that my answer to the first part is m is equal to 0.4 times E. For the second part, I want to find the weight on Mars of a person who weighs 100 pounds on Earth. This is telling me that I don't know M, but I do know that E is equal to 100. So I'm going to bring down this equation that I already found, m equals 0.4 E, and I'm going to just plug in that 100 for E to get m equals 0.4 times 100, which tells me that m is equal to 40. So a person who weighs 100 pounds on Earth weighs 40 pounds on Mars, and we should answer this with units. 40 pounds. Going down to the next problem, this is of a fairly similar nature, but not exactly the same. We're told that wavelength and frequency are inversely related, that W varies inversely as F. So the first thing that we want to do is set up our relationship. W is equal to some constant of proportionality divided by F. Remember, inversely means that we divide instead of multiplying. Then what we're given is essentially two separate ordered pairs. We're given a value of F, a frequency of 1200 kilohertz, that goes with a wavelength of 300 meters. So this is one ordered pair. W equals 1200, or sorry, F equals 1200 when W equals 300. Then we're given another ordered pair. What is the length of a wave? So what is the length tells us that we don't know W in this case, with a frequency of 800 kilohertz, so that frequency F is 800. If we map out all the information like this, it makes it so much easier to get through the problem, because the biggest mistake is when people are going back into the word problem to pull out numbers. They're having to rethink everything, and it's really common for something to get plugged in where it shouldn't. One important thing to keep in mind here is that this 1200, 300 is one ordered pair, and this 800 and I don't know what is another ordered pair, and that we never mix and match. I would never put this 800 for frequency with the 300 for wavelength from the first ordered pair. So what I'm going to do is use these first ones to find K, And then I'll just bring k across to the other ones. So we use these to find k. And then k is the only thing that comes across this line. Neither of these two values, the 1200 or the 300, are allowed to cross this line. So plugging in, we get 300 equals k divided by 1200. When we multiply both sides by 1200, we get a big number. Looks like 12 times 3 is 36, and then count the zeros, 1, 2, 3, 4. So 360,000 is equal to my k. So my relationship here is W equals 360,000 divided by F. And I can plug in 800 for my F, and I don't know W, so I'm going to use this to find W. So 360,000 divided by 800 comes out to be, I think, 450, because a factor of 100 drops out. So we get 3,600 divided by 8, and yeah, that is 450. 450 is a value of W, which is wavelength, which is measured in meters. So my answer over here is going to be 450 meters. One important characteristic of inverse variation is that as one of these variables gets larger, the other gets smaller. So it's sort of the opposite of what we see with direct variation. And we can observe that in these numbers if we just take a moment here. When F is 1200, W is 300. When F is 800, that frequency got a little bit smaller, and my wavelength, 450, was a little bit bigger than that 300. So this inverse relationship, there are a lot of things that satisfy this kind of inverse relationship. One fairly common example is the number of people working on a job versus the time it takes for the job to get done. If you have lots of people working on it, so the number of people increases, then the time it takes to complete it decreases. That would be a fairly typical kind of inverse relationship. There are lots of these in our everyday lives. Distance, rate, and time. If we also just think about distance, rate, and time, we've got distance equals rate times time. That looks kind of like a direct variation, but if we solve it for r or t, like if we do rate equals distance over time, this is an inverse relationship. So you would imagine the distance would have to be constant. If it takes longer to get there, then that means our rate was slower, and vice versa, right? So lots and lots of things in our everyday lives satisfy these inverse relationships.